always have to rearrange my windows here. Okay. So we mentioned 4 types of lamps, right? Sources for UV vis. These are 3 of the ones that are sort of interesting to look at. So in this first one, if you had to take a guess, which one is this?
Tungsten.
Tungsten for sure. Right, and so this is our tungsten lamp. Notice again how all this coil is very tight, right? This coil is as close together as those turns can get without touching each other. We don't want them to touch each other because you can actually cause the wire to melt if you have that current that touches at another point. So just about as close together as we can get those coils without them actually touching. So we have a nice tight region where that light is being emitted from, easier to contain it as we try to collimate it towards the diffraction grating. Let's switch now all the way over to the one on the right that looks like kind of like a minion. Which one did we say that was?
Deuterium.
Yeah, that's our deuterium lamp. And so inside this nice little metal box here is the deuterium light source. It's a spark, not a spark, it's a discharge light source. And there's a little window in that metal box here. I don't know if you can see it, but there it is. And so all of the light comes out of this quartz. Remember, this window here is quartz, while the rest of that envelope is glass. So it's a funny looking little bulb, but that's how we get our that's how we get our UV lights out of that enclosure. This one in the middle, is that an LED or is that our xenon flash bulb?
I'd say an LED, just a guess.
Anyone else?
Maybe it's, xenon.
Hey.
Xenon bulb. Yeah.
I had a 50-50 chance, darn it.
So LEDs tend to be solid state. That is, they don't require any glass. They don't require any kind of, they don't have to contain anything because it's just a single little electronic component that happens to emit light. In this particular one, you can see here this sort of joint. And so this top piece is the quartz, right? And then the rest of it's glass. It's a smaller package than the deuterium lamp, even though I've kind of made them all the same size. That quartz window is about the same size as the quartz window on the deuterium lamp, right? And so these flash bulbs are quite small. I don't know if you can see it, but there's two different electrodes, right? There's one there and there's one there. And so we just arc a spark between those two, and that's what gives us our flash for the xenon. And we only have to do that a few times per second while we're taking our measurement. Just neat to see those. We will see this guy and this guy when we take apart a UV vis. I'm not taking apart the brand new one, so we won't see the xenon flash bulb until the one we have runs out and I get to keep the dead one. Okay, so moving forward into monochromators, we talked a good bit in chapter 3 about sort of monochromator theory and how it works. And so I don't really want to say a whole lot here, except we still have the 2 different options where we could have prism monochromators, or we could have diffraction grating monochromators. And of course, we know that usually diffraction gratings provide higher resolution in a smaller package. The textbook goes into a little bit of detail about exactly how the geometry works, but again, we've seen most of that in chapter 3 already, where you have the entrance slit, and then the collimating mirror hits the diffraction grating, goes to the focusing mirror, and goes to the exit slit. And so, you know, I don't want to repeat myself too much, but we know what monochromators look like, and we know how they select. As you saw in the Lambda Max figure last time, that one had a bandwidth of 6 nanometers. On the exam yesterday, our UV-Vis had a bandwidth of 4 nanometers. Did you get that one right? And so, you know, these kind of bandwidths are pretty standard for UV-Vis. And so for, let me say, not exactly research grade UV-Vis, because usually those have a little bit better, a little bit tighter bandwidth. But you know, I would say anywhere from 2 to 6 nanometers is a reasonable bandwidth. Okay. All right. The last thing for us to discuss are detectors. And so when we are detecting light, we will always use a detector that converts light energy into electric energy. The word I wanted for light energy is radiant energy. Sorry, it just wasn't in my brain. Right? And really what that means for us is a way of converting photons to electrons. Have y'all heard of the photoelectric effect? Yeah, and so that's actually what Einstein won his Nobel for, the photoelectric effect. Everybody thinks it's relativity, but no. And so in this photoelectric effect, if we have a particular surface, usually a metal surface, that surface holds on to its electrons very loosely. Right? And so when a photon of high enough energy hits that surface, an electron will pop off. We have to have some pretty high energy electrons in order to do that. But luckily for us, UV-Vis electrons do have pretty high energy, relatively speaking. We couldn't necessarily use photoelectric kind of detector for infrared photons even, because they just don't have enough energy to pop off an electron. And so in this little diagram here, we have some photon coming in, and then this scintillator, it's just a material that when light hits it, it emits light, right? It's kind of like just something that will help propagate that light into the detector. This photocathode is our piece of metal where that photoelectric effect occurs. And then these dotted lines are electrons. And so for that photon coming in, we get 1 electron off. And these dinodes, these surfaces here called dinodes, they are a metal that will sort of exchange one electron for two or even three electrons, right? And so you're able to get multiple electrons out for every electron you put in. So we call it sort of the avalanche, the electron avalanche. Because we start with a single photon and a single electron, and by the end, you know, we could have 1,000,000 electrons or something. And so we really collect a bunch of electrons at every dynode. Right? And so this electron avalanche, each dynode emits multiple electrons. For one incident electron, right? Okay. And so, you know, 10 to the 6th is not an unreasonable number. So we get 10 to the 6 electrons for every photon. Keep in mind, you need a whole lot of electrons to really see some signal. And so we still need more than one photon. These detectors are not going to detect individual photons. Okay. And so for this one with 7 dynodes, right, that's where we might see millions of photons. For ones that have fewer dynodes, of course, we're going to see fewer photons. The one that we will see when we take apart a UV vis has just a single dynode, and so you only get a factor of maybe 10 magnification. But we're going to take apart some pretty simple UV vis that are not meant to be sort of ultra low detection kind of instruments. Okay. All right, I feel like there's a picture that's going to pop up that's going to cover up lots of my writing. Yeah, there we go. Not too bad. So this is a diode array detector. Let me sort of draw a line there. There's a diode array. Okay. LED, I don't know if you remember, stands for light emitting diode. Right? If we can wire it up to emit light, we can also wire it up so that it converts light back into energy, right? So into electricity. So LEDs convert electricity into light. These detector diodes convert light back into electricity. And so this particular one is real small, obviously. And let me see. This image is from our textbook. I'm going to see real quick if it tells us how many diodes are in here. It doesn't say. Okay, so you know, this probably has on the order of you know, 200 little diodes on this chip, right? But you can have larger or smaller ones to have more or fewer individual diodes. And so for a diode array, each diode collects a range of wavelengths. And so your bandwidth is actually limited by how many diodes you have. The more diodes, the fewer wavelengths go into each diode, right? And so you have a smaller bandwidth. And so an increased number of diodes means a smaller bandwidth. In a diode array instrument. So a diode array instrument is set up a little differently. Let me jump to the next slide here, where we talk about instrument variation. So just to sort of set the stage, right? When we talked earlier, let me go back to our slide on box diagram. Right? Here we have a source that goes into a monochromator. We get a single wavelength out that passes through the sample. What passes through the sample goes to the detector. In a diode array instrument, the monochromator still exists, but it's, instead of being before the sample, it's after the sample. So in a diode array, you got your source, and that source radiation goes straight to the sample, then to the monochromator, then to the detector, and to the data analysis and readout. I'm just going to say that that's a computer. Okay. Now this has a few implications for us. Right? In a diode array, first off, are we passing just a single wavelength through our sample now? No, right? We're passing all of those wavelengths. And so we're sort of testing the absorbance of every wavelength at the same time. And so all wavelengths pass through the sample simultaneously. But with a diode array detector, what happens is we're also able to detect all of those wavelengths simultaneously. And so the monochromator in a diode array looks a bit differently. I'll just sort of sketch it out real quick. Right? We have our incoming light that goes into our collimating mirror. It's going to hit our grating. That's then going to, diffract, of course, different colors at different angles. Right? Let me throw green in there. And what we do is we set up our diode array at the end, right? So we don't need a focusing mirror. We don't need a actually, yeah, sorry, we do need a focusing mirror. But we don't have an exit slit, right? That light is just focused onto our diode array detector. And so you can see how if you have more diodes, you're going to be able to sort of fine tune which wavelengths you're looking at better. If you have better linear dispersion with your diffraction grating, you're going to be able to spread it out better as well. But we have to make sure that we match those. We don't want to have such a wide linear dispersion with our diffraction grating that our diode doesn't capture it all, right? So we have to match the linear dispersion of the diffraction grating with the actual physical dimension of the diode array. And so essentially what this means is that we can get, because we can detect all wavelengths simultaneously, we're talking at sort of on the order of 1 second per scan, right? Whereas if we use a grating monochromator that just has a traditional detector, we will, it'll be sort of 1 second per step of that grating. And so, you know, if you're going the whole 600 nanometers from say 200 to 800 nanometers on a UV vis, and it's in a 4 nanometer bandwidth, that's 200 steps. So you're talking about 2 or 3 minutes of per scan versus 1 second per scan. And so diode array instruments are becoming much more common because of that, because just that speed that we're able to take that scan with. The little tiny UV vises that we used in lab last week, right, those are diode array type because you put your sample in, you hit scan, you get the whole thing immediately. There are very few diode arrays that are considered research grade for a couple of reasons. The first is that for a long time, they couldn't make diodes small enough, physically small enough to fit a whole bunch in to an instrument and not have the instrument be, you know, the size of a ping pong table, so that you get good dispersion from your grating. The second being that diodes generally are less sensitive than other types of instrumentation because they just didn't, for a long time, they didn't amplify the signal as much. And so if you had really low concentration, you know, it wouldn't necessarily pick it up. And so that has started to change. So if we're unable to pick up really low concentrations, which one of our figures of merit means it is not great?
The sensitivity?
The sensitivity, absolutely. And so diodes tend to have lower sensitivity than other detectors. But that is changing, of course, as electronics improve. And so lower sensitivity, but much faster. Right? Much faster. And because there's because you don't have to rotate your grating, right? Your grating is fixed because it's just shining on that diode all the time. And so there's fewer moving parts. So it tends to also be cheaper. And of course, the fact that there's no moving parts also means that it's more rugged. When we talk about the ruggedness of an instrument, we sort of talk about how fragile it is, how delicate it is. You know, can we take it out to the river and collect a sample and run a sample there? And so there's not a, you know, lots of the instruments that we will talk about are not rugged in that sense. you're not going to find a whole lot of people who take a mass spec out to the river. But you know, they do make these little UV vises that we've used. They do make an IR that's meant to, you know, take out to a crime scene or something, so you can have pretty fast analysis. But anyway, when we talk about ruggedness, you know, we're talking about how easy it is to transport, how easy it is to take out with you, and still operate at the expected level. Okay, so that's a diode array. The last thing that we'll talk about in terms of instrument variation is a dual beam. A dual beam spectrophotometer. These were sort of the standard in the 70s and 80s and up until the 90s, when there were still lots of concerns about the instability of light sources. Right? And so a dual beam, you have your source. We just draw out this box diagram real quick. It's the traditional setup where we have our monochromator before the sample. But what happens is, before it goes to the monochromator, before it goes to the sample, we have a splitter. And so half that light goes to the sample, and half that light goes to our reference or our blank. And then depending on the instrument, sometimes there's two different detectors. Sometimes they get recombined into the same detector. The one that we will take apart has two detectors, so that's how I'll draw it. And this splitter is not a beam splitter in the sense that 50% of the light goes one way, 50% of the light goes another way. This is what maybe it's more accurately called a beam chopper, because it's this wheel that has three sections. One section is blacked out so that there's no light that goes through. That helps us sort of zero our detector. Right? One is a, what color is a mirror? I don't know, blue. One's a mirror. To, you know, direct the light to the sample, for example. And then the last third is just open, so that it can go to the reference in this case. And so your computer has to know the position of the chopper so that it knows whether it's measuring the sample, the reference, or the black background, right? The zero light instance. And so if we look at it in time, so signal versus time, let's say we start at the black, this blocked out part, and we have our reference, right? Should be a high absorbance or a high signal, and then our sample is a lower signal, and then it's black again, and then our reference, and then our sample, and it's black again, right, et cetera, and it just repeats. And every time you have a turn of this chopper, the computer is doing an automatic background subtraction. And so instead of doing one background and then taking data for 10 minutes, you're taking a background literally, maybe once a second or something, depending on how quickly that chopper turns. And so doing this eliminates or greatly reduces, but I'll say eliminates because it does a very good job. This eliminates fluctuations in signal due to source instability. Okay. Additionally, any of those long-term environmental noises that we talked about, people walking down the hall, the elevator going up and down, if you have a really long scan for some reason, it would help to mitigate the fluctuations caused by those sources. And so these are still made. These are still sort of the gold standard for research instrumentation. They're very expensive because you have to have, there's a lot more moving pieces, right? You have to have a chopper. That chopper has to be sort of exactly synced with the computer, so you know at exactly which point that chopper is at each second. You have to have detectors. Most of them these days have dual detectors rather than recombining them. And so you have to have detectors that are matched in terms of their response, so that one isn't amplifying by an extra 5%, which would throw off your comparison between the two. You have to make sure that the light in each path travels exactly the same distance, so that they both reach the detector at the same time, whether it's going through the sample or through the reference. So the computer, again, knows exactly what's going on, when to take data from which detector. And so, there's just a lot of engineering that goes into making an instrument like this. And so these are by far the most expensive UV-Vis that are out there, but they also give the most stable data and often the most accurate. Okay. Quick review kind of question for you. I said, let me draw a line here. I said that this was the reference and this was the sample. If the reference is generally not colored, right? We think about doing a UV-Vis, that our blank is often water or whatever our solvent is. And so if our reference or our blank is a much higher signal than our sample, but yet we zero the instrument when the blank is in there, right? That's what blank means for us. So why would it have a higher signal than the sample here? What exactly are we measuring in the UV-Vis?
Absorbance.
So absorbance is what we get out, but is that what the detector is actually measuring?
Transmittance?
Yeah, it's measuring the power transmitted. And so our blank solution, the solution without any analyte, should transmit a whole lot of power through it, right? That's why our reference is so high and our signal is so low, right? So again, the reference has a large signal because it's the power that goes through it that we're actually measuring. Right? I'll put down here in parentheses power to remind you of that. Okay. The dual beam actually, because it has this blackout region, right, it allows you to subtract any noise that is just in the detector. We call it sometimes black signal or dark signal. And that's just any noise that's inherent in the detector that we can subtract that out as well. Right? So this level here is what we call the dark signal. and allows us to correct for any noise in the detector. Okay. All right, that's chapter 6 for us. Any questions about that, Caroline?
What is like is a diode just anything that goes between light and what is it, like electricity?
Electricity?
Electricity.
No. Diodes have much more uses than that when we think about electronics. But what they do is diodes sort of control the flow of electricity. They allow electricity to flow in only one direction. And so a light emitting diode takes electricity and forces it through this component, this material that emits light when the current flows through it. And then a detector diode has electricity that flows through it constantly, but when light is shown on, again, the material that electricity flows through, the current changes based on how much light is being shown on the material. They have other uses that are sort of, they're like the traffic cops of the electronics world. And so they don't have to have anything to do with light, but they have developed these particular types that can either give off or absorb light.
Okay, thank you.
Mm-hmm. Any other UV Vis kind of questions? Okay. So, let me see. I'm going to stop sharing my screen here in just a second. Well, fiddlesticks. I closed the window. Let me pull up our report. So, the oral report for us, and I will post these requirements to Moodle. All right. The oral report, again, these are going to be the week after Thanksgiving, and so we have lots of time, but I want to go ahead and give you these so you can be thinking about it as we go through the semester. 10 or 12 minutes long, and that includes some time for questions. And so, you know, if you're a little bit shorter than 10 minutes, that's fine, as long as we have a few questions from the audience. You have to have 3 references. Our textbook is good. Journal articles are good. Whoever makes that particular instrument, or multiple manufacturers, if you find that there's some competition, those are all good sources. In your actual talk, you have to have some kind of block diagram, right? We've drawn several here today. We will draw several more. And so just a simple block diagram that sort of shows the flow of whatever it is that's flowing. Today we're talking about the flow of light. When we talk about mass spec, we'll talk about the flow of ions. When we talk about NMR, we'll talk about the flow of microwave, radio signals. And so, you know, whatever is flowing is what we want to sort of watch through that block diagram. Have a discussion about why this instrument's better or worse than other instruments that might measure similar data. Oftentimes there's, you know, sort of very specialized instrumentation that can do something very well, but that's very expensive, kind of like the dual beam that we just talked about. Whereas a diode array collects very similar data without as good resolution or without as good stability, but it costs, you know, 1/20th the price. And so, you know, what are the advantages or disadvantages over other instruments? And then give an example of a particular experiment where that instrument would be useful, where the data collected is meaningful. Okay. So that's in your talk. Additionally, I want you to generate and produce some kind of infographic that goes along with it. I'll post an example or two to our Moodle page, as well as some links to websites that are fun to use to make your own infographic. And really, it can include a lot of the same information as your talk. And so I don't want you to reinvent the wheel. I just want you to have something to hand out so folks can follow along during your talk. Let's see. For exam questions, part of our final, so the ACS final, we gotta think really about what we're going to do there. My hope is, my thought is right now that we will take it before we leave for Thanksgiving, because we'll be done with most of the material that I want to cover by Thanksgiving. I think we may go ahead and take the final that Tuesday in lab. We'll see sort of how we progress rather than trying to do it online. So then during our final exam period, it would just sort of be it's not really an exam, it'd be a quiz almost with a question from everybody's instrument. And so what I want is 2 questions that you submit to me along with what you think the right answer is. And then I will, of course, add a question for every instrument as well. So if I don't think your questions are hard enough, I'll write my own. That's the oral report. I will also figure out how to post the options to Moodle in such a way that we can sort of select the one you want, and then it blocks other people from choosing it. I don't know exactly how to do that in a Moodle quiz yet, but I will figure it out. So this is a small list of topics that we will not talk about explicitly in class, that you could do your discussion on, your talk on. If you see one that's not on here, that you are particularly interested in, that we aren't going to talk about in class, by all means, let me know, and we can discuss and see whether or not it's a good topic. Because this is, like I said, not a complete list. It's just some of the more common instrumentation that we will not talk about this semester. So there are some good options there, but if you see something, if you don't see something that you want to do, let me know what you're interested in. Okay. All right. And then Journal Club, if you are on our Moodle page, one more share, I guess. If you're on our Moodle page, I put journal article number 1 here, micropads and colorimetric analysis. This is a neat paper by George Whitesides out of Harvard. He's an organic chemist. He's very well known in the organic community, but in the 2000s and 2010s, he spent some time working on problems in third world countries, and some easy analysis that anybody can do in the desert of Africa. What can we do about it? And so this paper is talking about, here's a very simple instrument. It has a couple LEDs that will tell you the concentration of whatever it is in your urine sample. Anybody can look at the LEDs and the screen and write down a number and see if it's in the range or out of the range, right? A very easy instrumentation. So it's a really neat paper. I also put, just if you're interested, his main paper on micropads, paper-based analytical devices, pads, PAD. But these are just little pieces of paper that have channels for liquid to flow, and you can put different test reagents in each of those wells. so that you can get different, you can test for different things in the same sample based on how it reacts with in a different well. And so this is his method paper for how he developed these. They get pretty complicated. There's a 96 well plate on paper. This is one where it actually flows through multiple layers of paper. It's really neat, and it's just he's a really ingenious dude, George Whitesides. And so, you know, that's just if you're interested kind of paper. The one that we will discuss most is this colorimetric analysis one. And so for a journal article talk, really what I'm looking for is sort of your reflection on you know, why this paper is interesting and useful, and you know, how it contributes to the world of instrumentation and chemistry as a whole. And so what I want from you, and I'll add it to Moodle as an upload, is you know, just a short paragraph that kind of summarizes what the paper talked about, just so I'm sure you read it, and then a short paragraph of your response and your feelings about it. I'm going to have that due at 8:30, so that you can't, you know, listen to everybody else's comments and then write your own and turn it in later. And so it's going to be due right at the beginning of class on Friday. Hopefully it doesn't take too long. It's a pretty simple paper. I don't want you to get bogged down in electronics and, you know, all that kind of stuff. I want you to sort of look at it for what it is, a pretty neat technique to measure something that has a pretty broad impact. Okay. Questions about either one of those things? Okay, so journal article due Friday at 8:30 a.m. And then the oral report will be that last week of the semester, November 30th or something. Okay. So a long time for that, but I just wanted to give it to you so you have time to work on it. Of course, I will remind you before we leave for Thanksgiving if that's when you're going to do it. Okay. All right. Enjoy your Wednesday.
Thank you.